Hi, it's teardown time again. We've got this beast, the Rohde Schwarz MXO4 series, the world's fastest oscilloscope. I've already done an unboxing and first testing of this scope, so I'll link that in down below if you haven't seen it. But you know what to say here on the EEVblog, don't turn it on, take it apart. Inglorious 4K resolution. Oh, hi to all my Romanian viewers. Beauty. So on the back looks like we've got 4 big ass screws here and a giant fan in this thing. It is whisper quiet. I'm telling you, the most underrated feature of any benchtop test equipment is a quiet fan. And oh, it's just beautiful. It looks like we've got some screws on the handle as well, but apart from that, should pop off. But yeah, there'll be a metal can inside here, no doubt. Or 1.5 gig bandwidth, 12-bit ADC of it. Oh, thing of beauty. Joy forever. That gonna pop off? Not without a fight. Oh, there we go. Well, that didn't help at all, actually. So I'm not sure what the deal is. There we go, but that's... I expected metal there. I expected more bang for my buck. Aha, gotcha. And I'll tell you what, I didn't know these legs extended. Isn't that neat? I've been using it but it hasn't fallen over yet, so nice touch. Wow. Oh, this is the best part. Oh, look at that. Prepare to be underwhelmed unless you're a metal case aficionado. There you go. Well, that is shielded. I don't actually know why they've got these giant cutouts here like this. Not sure what the deal is. They've already got the grate there for the all the air vents on the side, so not sure what that's doing. But damn, there's a lot of shielding on this sucker. It's an extra bit of metal there that goes under. I wonder what that's doing. Let's have a look. That actually slides off. Aha! That is a USB interface. And that'd be the LCD, but there's like a USB cable. Is this so that you can get easy access for... well, you can do the firmware upgrading. Firmware upgrading is really nice on this. You can do it via USB stick, or you can do it via the network. Yeah, that's just a micro B. Some reason to access... I'll have to see where that goes, but there's some reason to access that after the case, after all the metalwork is on. Oh, it's reveal time. Here we go. Got to watch yourself. You don't cut yourself on the sharp edges and whatnot. Okay, looks like I do have to get that USB out. Looks like we're going to have to get these cables out first though, but that is terrific. Maybe that's why. Maybe that's just an assembly thing at the end rather than having to access programming or something. Yep, there you go. And that's the reason that they have that cutout, is just for easy cable management. Very nice. Let's see the PCB. Oh, we've been mooned. We've been mooned. We've got just the bottom side of it. But, oh, beautiful. I was going to say, are these metal cans on the other side of here? It's like, I haven't seen like silkscreen like that on the bottom without it being associated with like a metal can on the top. But obviously, this is probably the main... the main ASIC that's doing all the magic inside this thing. Got a die-cast alloy. Look at that, die-cast alloy block. Oh, beautiful. Oh, look at those power connections. Seriously? That's pornographic. Demonetized. Well, yep, that has well and truly set the benchmark for oscilloscope power connections. 12 volts. And that's it. None of that Molex connector rubbish or anything like that. No. Oh, it's beautiful. A shake-proof washer, crimp, screw, PCB mount terminals. Thing of beauty. It's joy forever.
Behold the Wonkamobile. Thing of beauty is a joy forever. Places, please. The dance is about to begin.
Right off the bat, I've got to say this is the most gorgeously designed and constructed oscilloscope I've ever torn down, and it just gets better, right? I mentioned the die-cast alloy, cast alloy here, like front end shielding block, but then we've got the beautiful probe PCB here with a surface mount board-to-board interconnect there. So that's like, it's just beautifully the way they've done that and then screwed that into the die-cast case. It's absolutely fantastic. And then, but look at this. Look at this. All of the logic analyzer inputs are on one board here, and the test signals, and or pattern gen, sorry, and the test signal up here, and the USB interfaces are on these two gorgeous boards connected, and we've got RFI strips here and here as well, and they're actually connected through to a PCI-like board-to-board interconnect there, and they're screwed together with this huge custom metal plate here with massive screws and shielding and everything else. That is just, brings a tear to the eye. Brilliant. Hats off to whoever has done this. Absolutely fantastic. And then we've got a shielded block down here. That's all of our arbitrary waveform dual channel. Job in a single channel. Rubbish. By the way, this might be an early release one. I'm not sure if it's, I don't think it's quite pre-production, but this one is one of their showroom, early showroom instruments before release. So yeah, date of 2021 on there, 21st of the 10th, 2021, when this PCB was designed. So they had this board locked down for a solid year. Just, you know, refining it, working on the and everything else, the software and the firmware and operational and whatnot by the looks of it. So, yeah, wow, they've had it in the skunk works for a long time. Look at it. Just look at it. Look at it. Look at it. Just gorgeous. Oh. Ooh, there's a button I can push. There's just other really nice touches on this board. Check out the layout of this international rectifier DC to DC converter. That is a tight as layout. Look at it. It's just beautiful. And it's 45 degrees, so all the electrons are going to come out the right way. And then above that, we've got another one. Look at that. Ah, beautiful. Whoever laid out this board takes pride in their work, and they know what they're doing. They're our 10 megahertz in and out and external trigger. Well, to see all the goodness, we're going to have to take all this off. And to access the power supply as well, I think that's the first time I've ever seen that, where I've got to take the main board out in order to get to the power supply under here and even the fan. So, yeah, that's just an interesting, they've got it, you know, totally backwards to the way everyone else does it, but it's brilliant. Look at the beautiful attention to detail on the metalwork and all the grommets and the cable clamps here, and of course that that dedicated production cutout we saw in there. And then we've got a dedicated shielding enclosure, once again with RFI conductive foam there to go against the connectors to ensure a beautiful seal. And this is all. This has got a insulating sheet on it as well. Oh, beautiful. Just got more RFI sponge here. Oh, they love the stuff. Then again, that's not surprising considering Rohde Schwarz are basically, you know, one of the, if not the RF company. And that's why this thing has the best and fastest spectrum analyzer built into any scope. So yeah, they just know their stuff in the RF domain. And there's the bottom side load of our dual ARB waveform gen. So not much doing there. Just maybe regulation and other miscellaneous stuff, but yeah, all the interesting stuff's on the top side, but that'll just be like an FPGA or an ASIC. Oh, best probe interface solution ever, I deem that. Anything on the bottom? Got a few itty bitty parts on the bottom there. Wow, can't even see them. Look at it. Look at it. Die-cast alloy. Whoa. Ooh, it's got a port. Ah, found out what the USB was. Touch interface. Okay, the board ain't budging. I think this is screwed down here. I have to take off the standoffs from there. They might be screwing down into a standoff on the chassis. Actually, I don't have to take the ones on the side off. I think I can just, yeah, I can just lift it off. Oh, look, look, look at it. Look at it. Beautiful. Will it lift out? Oh, yeah. Oh, yeah. Look at that. Oh, what a Bobby Dazzler. Ta-da! Oh, I'll show you up close soon, but, oh, wow, look at the inside of that. Beautiful. And well, yeah, it looks like the world's fastest oscilloscope and the world's best designed and assembled oscilloscope has got the world's lowest noise fan. I haven't looked up the data sheet. This is a noise blocker NB loop. Oh, you'd have to put up the data sheet for that one. I'm sure it's a Bobby Dazzler. I'm sure it cost an absolute fortune. And little rubber baby buggy bumper compliant mount as well. Look at the compliant mount. Look. Oh, I play with that all day. So I haven't even looked up the brochure for this data sheet for this fan, but yeah, you can see like it's got the edges on this and it's got slightly like scalloped edges on it as well. This is all to reduce the fan noise. Oh my god. Oh, frame rate, it's going backwards. Ooh. This is so utterly pornographic they should be charging a subscription on OnlyFans. Well, it turns out that actually none of these devices which have the... This is actually silver. This isn't silk screen. It's actually a silver-plated board. I've done previous videos on that. Turns out none of those are actually shielded, although they've put the ability for them to be shielded. You can see like shielded cans can actually go over that, but they put it in the design stage and went, nah, we don't need that. So obviously what we've got going on here, you've got your four front ends, you've got two ADC chips. I think it is shared. So yeah, that's common in all designs. So I don't know if that is a dual ADC or it's a single ADC and then it's got a MUX in there. I can't actually remember. And this is the new bad boy ASIC that's responsible for the world's fastest updating scope and obviously FPGA applications processory thing over here, whatever it is they're using. Clock gen in there. It's a dead giveaway when you got a couple of oscillators in there. That'll be like a PLL or like a clock gen for all the sampling. So that'll be doing all that. And here is our sampling memory, huge amount. Can't remember what, but anyway, that'd be top of the line. It's interesting that it's got like 6 of them, and sort of like these 4 seem to be physically arranged together. We'd have to check the size of that. And then it's got like 2 separate ones over here, so that might be doing holding for some other holding waveforms and stuff for other processing functions, the separate FFT or something. Don't know. There it is, nude, without the heat sinks or the shields. I left that heatsink on because it's exactly the same ADC over here. That's a TI 12-bit jobby, so that's not a Rohde Schwarz ADC. But here's the magic ASIC that makes it all possible. The 4 million waveform, 4.5 million waveform updates per second, and a Xilinx Zynq. Yet again, winner, and let's look at the front end. Looks really nice, and our waveform gens over here. I've taken, as always, high-res teardown photos available over on EEVblog.com, which links to my Flickr account, and you can see those, but let's go through it quickly. You gotta love taking off RF metal cans. I'll get back to you. Come on. Oh, look at that. Look at that. Got it. Ooh, that little port there. Just for the external trigger input. But look at that. For all you RF aficionados. There's the backside in glorious 4K. But high-res photos over on EEVblog.com. Ooh, I'm zooming in. Because I can. Oh, look at those isolation slots. 4K front end. Ooh, beautiful. All right, let's do a quick look at the analog front end here. I've got the top side of the board here, and I've got the bottom side, which I have flipped horizontally so that everything matches up. So what we've got here is our BNC input here, and this shielded can here, this is another relay under there. I'm not sure if it's the exact same one as that. It looks similar, but anyway, that one's shielded because it's right at the front end. Remember, this is 1.5 gig bandwidth on the 50 ohm termination side. On the 1 meg side, it's 750 megahertz. Now, this is all very interesting, right? We've got multiple paths. We've got paths going out here, whoa, and here, and we've got paths going through here, like this, through to the variable gain amplifier, which is a Rohde Schwarz jobby. We don't know It says RUS. I guess that's Rohde Schwarz. If you have any info on that, please leave it down below. Are they rebadging someone else's? I don't know, but it'd be a 1.5 gig bandwidth programmable gain amp. So yeah, very impressive, okay? So our BNC input comes in here, and then we're basically switching it like this, and then we've got our 50 ohm path like this, goes into this relay. We'll take a look at the data sheet in a minute, and then it looks like this second relay here splits it into two different paths there. That one has some sort of amplifier or some sort of buffer in there, something like that. I don't know. If you want to decode that part, knock yourself out, but the other input goes here. So these two would be different attenuation paths. So this is the full 1.5 gig bandwidth part here. I don't know where the 50 ohm terminators are, like the actual 50 ohm termination resistor, I don't know. But anyway, let's have a look at these Axiacom relays here. These are exactly what you'd expect. These are RF signal relays, DC to 3 gig bandwidth. They've got 50 ohm impedance, and exactly what you want. Sure enough, there it is there, measurement and test equipment. So yeah, there it is. A nice RF signal relay, 3 gig bandwidth. It does 50 watt power handling, but we're talking signal here. So yeah, no wuckers, exactly what you want. And then this other relay here, this is a different one, because remember, this is only 750 meg bandwidth part. This is all part of the 1 megahertz bandwidth channel. And sure enough, this is just a signal relay. It's not an RF relay as such. So it's not, 50 ohm impedance controlled. Everything else, because all of this is the 1 meg ohm channel. And if we have a look on the bottom side there, bingo, there's our 1 meg input resistor there. There's our AC coupling cap. This is our solid state relay here, which switches your AC DC coupling, and then it splits it into basically two different paths here. One goes through here like this, another then curiously splits like that. So they're not using the relay to switch that, they're just using different paths like that. And of course, these are the capacitors here are the coupling for the resistors on the top side here. So these will just have different attenuation ranges. So this is what you get when you hear the relays click. When you change the vertical attenuation setting, it's switching a different path in there for different attenuation, front-end attenuation settings, and then the programmable gain amp does the rest there. So, and that'll do software bandwidth limiting inside there as well. So that's no doubt a super secret analog front-end 1.5 gig bandwidth, pretty schmick. Now you might be wondering, what's the deal with these slots here? Are these for high voltage isolation, which is what you normally see? No, these are for, not for clearance, but what's called creepage. And I've done videos on this. You don't want any contamination on the boards actually, causing coupling between the channels. Because when you're talking about 750 meg bandwidth like this, they've gone to town just to make sure they're just reducing the coupling between here. And there is some reduction in there in capacitance as well. But yeah, basically, you want to stop the board gets contaminated or anything. You just want to minimize your capacitance across all these channels. So that's really nice. And they got the isolation slots under the relay there too. They didn't bother with the 50 ohm paths here because capacitance or leakage between channels in the 50 ohm low impedance path doesn't really matter because it's 50 ohm impedance. And all this stuff down here, this would all be offset control for vertical offset range. I think it has a phenomenal offset range, doesn't it? If memory serves me correctly. And of course, over here we have the old school 595 shift register for driving various stuff. You find it in every scope. It's absolutely amazing. Anyway, it looks like we have a differential amp here, and it looks like this is some sort of differential driver, perhaps? It looks like that's just driving the high impedance lines. You can see those over on this side here. These are the controlled impedance differential lines which bugger off to the ADCs up there. So yeah, are they like discrete parts? Maybe? It may be like a discrete transistor differential amp, perhaps? Don't know. And all the rest of it's just miscellaneous housekeeping stuff, so we won't bore ourselves with that, but yeah, nice front-end implementation, and you're paying for it, of course. And this is where the magic happens. This is their new XP for extra performance ASIC, the MXO4 ASIC, and it's responsible for the 4.5 million waveform updates per second, industry leading, and it would also do the digital triggering because it's got one of the world's best digital triggering systems in it as well. So that's really remarkable. So yeah, that'd all be being done inside that ASIC. So they've been working on that for donkey's years, I'm sure. Now the memory up here, as I said, look at how they group things when you're looking at PCBs, because the PCB designer usually groups functional blocks together. So the fact that there's a bigger space between here tells me that these are functionally a different block to what these are doing. That'd be my guess anyway. I'd love to have that confirmed, but I don't think it's any coincidence that they're, you know, these gaps here are even and these ones aren't. So my guess is sample memory and then something else, I don't know, FFT, digital logic analyzer, and, you know, stuff like that. So yeah, I've decoded the part number here and we can go over there. That's actually a Micron 8 gig bit. So that would give 4 gig bytes sample, but because this is a 12-bit ADC, we can't just store it in 1 byte. So it's got to be, it's need at least 2 bytes to store each sample in there, and this has got 400 meg samples. So yeah, there's plenty of that, and they have to do waveform storage and everything else. So there's more than enough memory in there, that's for sure. So what we've got here is the external trigger system. Now that that superb digital trigger system, the really sensitive one I told you about, it's not just for the external trigger, it's for the analog ones as well. So that's done inside the ASIC. And in here you can see the controlled impedance trace there. That's the 1.5 gig bandwidth going up to the ADC up here. Yeah, so this is just another 595, and there's an analog devices comparator down there. I won't look it up, but look, they've got the nice creepage slots again, very nice. So they're just switching in different paths there. And just the top side of that digital trigger, under my head there is the BNC input. Once again, we got ourselves a solid state relay there to switch the AC coupling, 1 meg input impedance. Then there's just got the paths going through there. What's over here? It's a TI jobby. I don't know, like not too fussed. Don't know what this contamination here in this board is. That's rather interesting. It's on the other side too, so I'm not sure what happened there. Once again, I don't think this is actually a production unit, so I'm not sure what's going on, but anyway, interesting. Some engineers spilt their coffee maybe. There's our ADC, isn't that sweet? It's a TI jobby. There's no custom Rohde Schwarz here. Let's go to the videotape. As I said, these controlled impedance traces coming in here, 1.5 gig bandwidth a pop. So let's have a look. So you can either implement it as a single channel or a dual channel here, depending on the bandwidth, 6.4 gig samples per second or 3.2 dual channels. And that's more than enough for the 5 gig samples per second on 2 channels or 2.5 gig on the 1. No worries. And that's got an 8 gig bandwidth, usable input frequency range greater than 10 gig. So I wonder how much that thing costs. I don't even want to check. Only draws 3 watts. That's all right. And the applications processor, Xilinx Zynq. We just see it everywhere. Ultra scale jobby. And you can look up that individual part number, compare it with different oscilloscopes I've done. Couldn't be bothered. Xilinx Zynq, like they win practically every oscilloscope. Almost every. Name an oscilloscope I've torn down in the last 5 years that doesn't have a Xilinx, some variation of the Xilinx Zynq in it. Obviously, this is probably going to be one of the beastiest ones because this sucker is really quick. But of course, all the grunt work is done in that custom ASIC. So yeah, that's a combination of FPGA, of course, but it's got the ARM cores, like multiple ARM cores doing their ARM thingy. Unit price, $3,000, one off, no stock. Gosh darn it, Rohde Schwarz bought them all. Yeah, down here it says it's got a quad ARM Cortex core, dual ARM Cortex R5 with core sight, and an ARM Mali as well. How many bloody cores is that? Unbelievable, you can't even count them on one hand. Quick look at the arbitrary waveform generator here. I expected like some sort of little CPLD or ASIC under here, but we don't. So that must be handled by the Zynq, maybe. or maybe the MXO4 ASIC, not sure. But anyway, there's a TI DAC there. Won't look up details. More 595s, they're everywhere. Another little DAC here, so that'll be maybe doing some offset or something like that. So yeah, this is dual. You can see the path going out there. So this is the main dual DAC for doing that. Yeah, but there's no associated logic with that. Anyway, lots of relay switching, and then you got your 50 ohm output impedance, and you got all sorts of stuff. So, but yeah, that is dual 100 megahertz bandwidth, not like 20 meg rubbish. And here's some power supply stuff down here. This is the inputs down here, the 12 volt inputs, and oh, look at Atmel. Oh, the Atmel fanboys go wild. Oh wow, wonder what that button does. Might have to try it. Anyway, how cool is that? That is one beast of a board. I can't go over every single detail. As I said, high-res photos over on EEVblog.com. Check it out. But yeah, hats off to Rohde Schwarz. This is one of the best designed and built scopes I've seen. It'd want to be. It's pretty pricey. Starts at about $7,000 US, something like that, and goes up depending on your options. But the world's fastest oscilloscope. It's absolutely nuts. The only issue I have with the teardown is the plastic handle. Even aren't Xilinx doing metal handles now? Oh, come on. Anyway, I hope you enjoyed that video, found it interesting and useful. If you did, please give it a big thumbs up. As always, discuss down below. Oh, and by the way, I'm now uploading all of my videos natively on Twitter. So if you want to watch them over there, can't upload this in 4K on there because they're only doing 720p's. They're recommended. They do 1080, but you know, they recommend 720. But I'm uploading videos natively there now. So hope to get subscription system up and running soon. They haven't approved me yet. Anyway, it'll eventually come. Catch you next time.